right, we're gonna go ahead and get started. So we talked about the first derivative test yesterday, or taking the first derivative. When we take the first derivative, what does it tell us about the function? It does two things. When we take the first derivative, we know what is happening to the function. We know what about the function.
Whether it's positive or negative.
Where the function is, on what interval it is increasing or decreasing. First derivative tells us on what interval the function is increasing or decreasing. And we can also tell what else from taking the first derivative. The max and mins, right? The relative max and mins. So the first derivative tells us where the function is increasing and decreasing. It tells us where we have potential relative or local max and mins. Today, we're going to talk about concav, or the second derivative test, or what effect the second derivative has. And we're going to start out by talking about concavity. So here we say that if we have a function f that's differentiable on an open interval, then the graph is concave up. Think about cupping up, like concave up. Or when the first derivative is increasing, and concave down when the first derivative is decreasing. All right? That's kind of the definition of concavity. Technically, concavity is related to the slope of the derivative, and I'll kind of show you that as we go down a little bit further. The nice thing about this, though, is that if I take a function and take the second derivative of the function and find out where the second derivative is positive, right? When I find out where the second derivative is positive, it tells me whether or not the first derivative would be increasing. If the second derivative is negative, it tells me where the first derivative is decreasing, just like the first derivative tells us that exact same thing on its function, right? It's one back, right? So if we have a derivative, and it's positive or negative, it tells me where the function is increasing or decreasing. We're kind of using that same concept here. If I talk about the second derivative, it tells me where the first derivative is positive, is increasing or decreasing, all right? So what that gives us then at the second derivative level is if the second derivative is positive, the function itself, two back, right? The function itself is going to be concave up. Or if the second derivative is negative, it's going to be concave down. The function is concave up, concave down. The derivative is increasing, decreasing at that point. Think about how far away you are, right? At the second derivative, we got something in the middle, don't we? Okay, so what you want to take out of this, that's how they're related. What you want to take out of this is I can take the second derivative. When I find out that the second derivative is positive or negative, I can conclude to the function that the function will be concave up or concave down. That's what we're going to get out of this. So let's start with something that's rather simple in that it is a regular old polynomial. (12 plus 6x squared minus x cubed). It's a polynomial. The function would be continuous, right? Okay. So we're going to start here and we're going to take the first derivative of this function. So f prime of x gives me 12x minus 3x squared, right? Okay. Now, we're interested in moving on past that. So now I want to know, what is the second derivative? The second derivative would have to be 12 minus 6x. Now, the second derivative exists. It is also a continuous function, right? There's nowhere where the second derivative does not exist. So we're gonna set the second derivative equal to 0 and solve. I would have 6 times 2 minus x is equal to 0. Or 2 minus x is equal to 0, x would have to be equal to 2. That's the critical value for the second derivative, right? The derivative exists, and that's where the second derivative is equal to 0. So just like before, we're going to test values around that critical value. So if I have 2 here, we're going to test, is the second derivative positive to the left of 2, and is the second derivative negative to the left of 2, to the right of 2? Opposite sides, right? So let's just pick 1, because that's to the left of 2, right? If I look at the second derivative, 12 minus 6x, 12 minus 6 is 6, which would be positive, correct? So the second derivative is positive. And therefore, if it is positive, it would be concave up. On the right of it, if we pick f double prime of, I don't know, 3, f double prime of 3 would be what? 12 minus 18? Negative. Okay, so this would be concave down. All right, it's just, where's the function concave up and where is the function concave down? Okay. Let's try that with something that's a little more challenging. Here we have the function h of x. H of x is equal to x squared plus 1 over x squared minus 4. Okay. Where is that function undefined? All right, so the function would be undefined. Is undefined when x is equal to positive and negative 2. In other words, those would be asymptotes, one would think. Okay, and if the function is undefined, or if we have asymptotes, then the derivatives will also not exist at those points, correct? Okay, but remember, the derivative cannot exist but still be a critical value, correct? Okay, but it's still important to kind of understand what those things are. So let's come in here and let's take the first derivative of this function. And h prime of x is going to give me, let's do the low-de high, high-de low today. All right, so low is going to give me x squared minus 4. The derivative of the numerator is 2x. Low-de high minus high-de low. So we're going to say minus the numerator, x squared plus 1, times the derivative of the denominator, which is again 2x, all over the denominator squared. Okay, let's simplify our numerator. So I end up with, what would that be? 2x cubed minus 8x minus 2x cubed minus 2x, correct? All right. X squared minus 4 squared in the denominator. So I end up with just negative 10x over x squared minus 4 squared. That's the first derivative.
Then we distribute the square. And like X.
In the denominator? I don't want to. Not because I'm lazy. It's not gonna get us anywhere when I take the second derivative. Okay, all right. So the second derivative then, H double prime, again, low D high, high D low. So we take low, which is gonna be x squared minus 4 squared. That's the low. D high, the derivative of the numerator is gonna be -10, correct? Minus high, -10x. Now let's keep straight here, keep me straight here. Let's take the derivative of the denominator. That's gonna be 2 times x squared minus 4 to the first power times 2x. Right, using the chain rule there, all over the denominator of x squared minus 4 to the second power that I am now squaring. So far, so good? Everybody saw what we did? Low D high, high D low, over low squared. All right, simplifying the numerator. Let's just take -10, I'm gonna write it in front. Let's write it as x squared minus 4 to the second power. Plus 10 times 2 times 2, right? Does everybody see that? 10, do you see my little, oh yeah, you do today. 10 times 2 times 2, it's gonna give me 40. X squared times,
You were before X squared.
okay, thank you. Times x squared minus 4 to the first power, all divided by x squared minus 4 to the 2 times 2 would be 4th power in the denominator, right? Yeah? Okay, so I have an x squared minus 4 that I can cancel out of the 2 terms in the numerator and the 1 term in the denominator, correct? Okay, so I'm going to do that. So I'm going to reduce that denominator by a power of 1, so that's going to be 3. This reduces to the first power, and that just totally disappears, doesn't it? Because I took out an x squared minus 4 from each of the terms in the numerator and canceled it with the 1 in the denominator. So this gives me -10 times x squared minus 4 plus 40x squared in the numerator, all over x squared minus 4 to the third in the denominator. And let's simplify the numerator a little bit more. -10x squared plus 40x squared over the denominator. So I would have 30x squared plus 40 over the denominator. That's the second derivative. Okay, all right. Now we know that the second derivative again does not exist at positive and -2, correct? All right. So here, it doesn't exist when x is equal to positive and -2. But the critical value for where the derivative is equal to 0 comes when 30x squared plus 40 equals 0, right? In other words, the x-intercept of that function, the x-intercept of the second derivative, yeah, is where the numerator is equal to 0, okay? So divide both sides, x squared, or I guess I would subtract 40 to the right. And then divide both sides by 30. I find out that x squared would be equal to -4/3. Can I take the derivative, or can I take the square root of -4/3? No. And get a real number? No? So then, remember that concluded then that there was no x-intercept, if that was my function, right? Because each one of these are their own function, right? So when we did rational functions, we knew that when I set the numerator equal to 0, I don't always have to have an x-intercept for that function, right? Okay, so this says that I have no x-intercept. So there is no x-intercept or no critical value here, right? There's no critical value there. So the only test points that I now have would be at positive and -2. I do need to test those critical values, okay? So we have -2 and +2. I'm going to test to the left and to the right and in the middle. So I want to know what your conclusions are. Tell me if the function is positive or negative. Tell me if the second derivative is positive or negative.
-2 is positive,
Okay, so we're positive. What about in the middle
negative,
and to the right?
positive.
Okay, so that conclusion then would be, we would be concave up where we're positive, concave down where we're negative. So the interval then, so here, we're going to write a conclusion about the function, not the derivatives, about the function. So the function itself would be concave up, CU is going to be concave up for me, on the interval from -infinity to -2, and then again from 2 to infinity. And we would be concave down, CD, then on the interval from -2 to +2. All right? Remember that the conclusion that we're going to make is a conclusion about the function that we started with. We take the first derivative to find out where it's increasing and decreasing and max and min. We take the second derivative to find out where it's concave up and something else. All of these conclusions are about the function that we started with. So now, just like a first derivative not only told me increasing and decreasing, but it told me where I could possibly have a relative max or min, concave up, concave down is also going to tell me at the point at which it changes from concave up to concave down. That's called an inflection point. The point at which it changes from going from concave up to concave down is what we call an inflection point. You can see here what we're talking about, right? So over here, I've got something that's concave up, and then it changes to be concave down. The point at which it changes is called an inflection point, and you can see that that's happening where we have a tangent line, right? We're crossing that tangent line in essence. So the concavity of the function changes at the inflection point, and it's where it crosses the tangent line. Here you can see we're concave down and then concave up. All right, that's what we're talking about. Tangent lines must exist at the point of inflection. Just because you have concave up and concave down does not necessarily mean you have an inflection point. That's what that means. So this then becomes important. Our test for concavity, we know the two of the bullets, but I want you to make sure you understand. We are going to suppose that the second derivative does exist at all of the points along there on that open interval. We already know that if the second derivative is positive, then you're concave up. If your second derivative is negative, then you're concave down. But the third bullet in there says if C is a point on that interval where the derivative changes sign, then you have an inflection point. But your derivative has to exist in order to have that inflection point. Okay? So above, the first example that we worked, right? The first example that we worked, let's pull that information down here for a minute, right? We said that for this polynomial, we had a critical value at 2, and we knew that the second derivative told me we were concave up, and then we were concave down. So because the critical value exists there, and I'm changing from going to concave up to concave down, we have an inflection point occurring when x is equal to 2. All right, we have an inflection point that is occurring when x is equal to 2. So let's just look for a second at what that means. So if we have our polynomial, which we said was 12 plus 6x squared minus x cubed all right, then we have here, let me turn these off. That's the function we're looking at, right? That's the function that we are looking at. That's the original function that we were looking at. It's a cubic function and it's going down. Now, what that says is here, right? Our second derivative test said that we had an inflection point at 2, okay? Is this the right function we have in there? Concave up? No, concave down. D dx, I don't think I have that one in there right. What is our derivative that we had? Our second derivative, yeah, 12 minus 6x. And it was occurring when x is equal to 2. What's that look like? X is equal to 2. There. That's what I wanted to show you. All right. Let me go back. Restate this. The purple line, it's because I can't see it. The purple line represents the first derivative, right? Second derivative. Purple line represents the second derivative, correct? Okay, where's the second derivative crossing the x-axis at? It's crossing the x-axis at 2. We discovered that algebraically, right? That's the x-intercept for the second derivative, correct? All right, now that x-intercept at 2 becomes the inflection point on the function, right? That point right there, when x is equal to 2 and y would be equal to some other number, 28, that's the point at which the function is changing from concave up to concave down. That's what the second derivative tells us. So when we're sketching these by hand now, we're going to know exactly the point in which it changes from concave up to concave down. Does anybody know anything about concavity and inflection points related to Statistics? No? No? All right, so statistics is based on calculus and our normal curve. Y'all remember the normal curve? Did you ever take statistics? No? All right, well then I won't go there. But that's important because it is actually this point on a normal curve in statistics, which is so many standard deviations away from the middle, which is kind of important for you when you're taking statistics to know that. That's what occurs there. But anyway, maybe you'll take another statistics class as you get further into your degrees. So let's move on then, and let's talk then about really quickly, what did we have for our other function up there? Remember that on this function, this rational function, we said what? We said that negative and positive 2 were critical values, right? Okay. We knew that we were concave up, down, and up. But what was unique about these negative and positive 2's? Does the derivative exist there? The derivative does not exist there. So although we have concavity, we don't have an inflection point. Okay, so you want to make sure that you're keeping track of whether or not the derivative exists at that point. Because if it doesn't exist at that point, right, then our function isn't going to have an inflection point, is what that means. All right. And that graph looks like this. That's the picture of that graph. See how it's concave up, then it's concave down, then it's concave up again, but nowhere in there, because there's asymptotes that are occurring here on the original function, nowhere in there does it actually change from concave up to concave down or vice versa. Okay, so you want to keep track of that. Okay. So let's practice then this part right here where I want to find the points of inflection and discuss the concavity of the graph. In other words, we're going to do the same thing that we did before. So my function that we're looking at says 2x squared times the natural log of x minus 5x squared. This function is continuous. The first derivative of this function is going to be the first term, 2x squared times the derivative of the second, because we have the product rule going on here, times the derivative, or plus the derivative of the first, which would be 4x times the second, minus 10x, all right? So I have 2x squared times 1x, 1 over x plus 4x natural log x minus 10x. Now let's simplify this. I end up with 2x plus 4x natural log x minus 10x, or 4x natural log x minus 8x. Product rule, right? Product rule. Does everybody understand what we're doing right there? Okay, that's the first derivative. So the second derivative, again, we have the product rule here. So it's the first times the derivative of the second plus the derivative of the first times the second minus 8.
or 4 plus 4 natural log x minus 8, 4 natural log x minus 4. Product rule for that function. So because we're talking about concavity, we're going to come in and we're going to set this derivative equal to 0. I'm going to say the natural log of x, 4 natural log x is equal to 4. Natural log x is equal to 1. Remember, we can exponentiate both sides in essence, because that causes those to cancel. And I found out x is equal to e. All right. Now, let's test this to find out where it's concave up and concave down. So I have E, and I want to test around E. So what are you going to find? All right, so we're negative to the left, and what about to the right?
Positive.
We're positive, so we're concave down as well as concave up. The derivative exists, right? There wasn't anywhere in there when the function didn't exist on what we're looking at. So we would say that we are concave up on the interval from what, e to infinity. Concave down on the interval from negative infinity to e. And because we are changing from down to up, looks like we would have an inflection point there. We would have an inflection point when x is equal to e, and the ordered pair comes when you substitute e into the original function to find out what the y value is. Let's look at another one here. So this one we have the cubed root of x minus 4. So that function's continuous. Remember, we talked about what that function looked like yesterday? Yeah, it looks like the cubic function rotated 90 degrees, doesn't it? Okay. All right, so what's the derivative? Well, I'm going to rewrite this as x minus 4 to the 1/3 power. And the derivative would be 1/3 x minus 4 to the negative 2/3 times 1. And the second derivative would be negative 2/3 x minus 4 to the negative 5/3. And we're multiplying times the 1/3 at the front, right? I just pulled my 1/3 down. So I would have negative 2/9 times x minus 4 to the negative 5/3. Or negative 2 over 9 times x minus 4 to the positive 5/3. So what does this tell me? First of all, the second derivative does not exist when x is equal to 4, correct? Second derivative doesn't exist when x is equal to 4. Now we want to know if I set that derivative equal to 0, is there an x-intercept? No, right? There's no x-intercept. So f double prime has no x-intercept. So the only critical value we're going to use in this case is that 4. And remember, the derivative f double prime does not exist here. So is the function concave up or concave down to the left of 4? Concave up. Is it up or down to the right? So the interval in which the function is concave up occurs where? Negative infinity to 4, we're concave down. Where? Do I have an inflection point? No, I have no inflection point. All right, let's work another one. Here I have the function f of x is equal to e to the negative x squared over 2. These are kind of fun to look at. I was wondering what these look like personally. So I would encourage you to go in and look and see what they look like. What is e to the x to the first? What is e to the x? First of all, what is e to the x? What does the graph of e to the x look like? What'd you say, Javier? Just do it with your finger.
Does it cross one?
Yep, so it was that increasing exponential function, right? What does e to the x squared look like?
Bump.
It looks like a bump, doesn't it? What does e to the x cubed look like on your graphing calculators?
It starts to bump and then shoots it.
So it's kind of a variation of this, isn't it? In essence, it's sort of ish. What's that e to the x? What did you do? You did x cubed, do fourth. It's a bump still, isn't it? To the
Really,
e to the x to the fourth.
yeah, it's really good. Well, it looks like a brown one.
What does the negative look like? We'll try that.
A negative x.
Negative x. Negative x squared. Negative x to the third. Jonathan, get your head up and put it in your calculator. Isaiah, are you putting this in your calculator? Did you turn in your homework?
Good paper.
Yes. There's a stapler up there. What do they look like? You getting a pattern? Do they have patterns, right? Yes or no? You getting a feel for what they look like? Okay, it's always better if you can have kind of an understanding, a base understanding of what you think the function might look like, right? It's kind of helpful. All right, let's go on. Let's take the derivative here. So this is, like Sam said, this is a continuous function that looks something like that. Well, a little bit better, but it looks like that. Looks like a wave. So the first derivative, so we know it's continuous. The first derivative is the chain rule. So we're going to take the derivative of e, which is e to the negative x squared over 2, and multiply it times its exponent, the derivative of its exponent, which would be, we'll pull that negative 1/2 out. The derivative of x squared is 2x. So the derivative of f, the derivative of this function is going to be negative x e to the negative x squared over 2. Using the chain rule. It's the derivative of the outside, which is e, times the derivative of the inside, which is the exponent. So the double prime is the product rule. So we would have negative x times the derivative of e to the negative x squared. We already found that e to the negative x, the derivative of that is the first derivative. Negative x e to the negative x squared over 2. So it's the first times the derivative of the second, plus the derivative of the first, negative 1, times the second, e to the negative x squared over 2. So simplifying this, I get x squared e to the negative x squared over 2 minus e to the negative x squared over 2. And I am going to set this equal to 0 and solve. The nice thing about setting things to equal to 0 is if I can get it factored, I take each of the factors and set them equal to 0. So I could factor out e to the negative x squared over 2 from each of those terms, and I'm left with x squared minus 1. Both of those are equal to 0. So e to the negative x squared over 2 equals 0. X squared minus 1 is equal to 0. Here I can take the natural log of both sides. And I would end up with negative x squared over 2 is equal to the natural log of 0. Can I have the natural log of 0? Remember, the argument always had to be greater than 0, didn't it? Okay, so that just goes away. But I can come over here and say x squared is equal to 1, or x is equal to positive and negative 1. So come over here and let's just test the concavity. So I have negative 1, positive 1. F double prime. Okay. Let's find out where that is concave up and concave down. So you found what? You found that this is, what is happening to the right of -1? Okay, so are we,
To the right of -1.
oh, directions, what's to the left of -1? Okay, so we are what? Concave up or down?
Up.
All right, and now to the right of -1 and to the next. Okay? So we would say that the function is concave up from -infinity to -1, and again from 1 to infinity. Concave down between negative and +1. The derivative exists, the second derivative does exist at those points, so we have inflection points then occurring when x is equal to positive and -1, right? Okay? And that's what that function looked like. So the red line is the function itself. And the green and the blue line represent the x-intercepts of the second derivative, or the point in which this is changing from concave up to concave down. That's what those are. The inflection points occur where the second derivative has critical value, where the second derivative has a 0. Okay. So determine where. Determine where the function is increasing, decreasing, concave up or concave down. Find local extrema, find the inflection points, do it all, okay? Summarize, in other words, what we've been doing for 2 days. We're gonna start with just this nice polynomial, yeah, 4th degree polynomial. It's a positive polynomial also, isn't it? What's the end behavior here? Goalpost, right? Goalpost positive, yeah? Okay, and it would be continuous along the function. So we kind of have a general idea from what we did in pre-calc. So I'm going to come over here and I'm going to talk about the first derivative. For the first derivative, we have 12x cubed minus 12x squared minus 12x. Wow, plus 12. It's the first derivative, right? Let's set it equal to 0 then and solve. What are you going to do there? Maybe we should factor a 12 out of all of that stuff, right? Let's try that. 12 gives me x cubed minus x squared minus x plus 1. Now maybe what do you want to try? Grouping. I've got 4 terms. I'm going to try grouping. Yep. So I'm going to group it in that way. So I've got a x squared I can factor out of the first time, leaving me with x minus 1 minus x minus 1, because I have to change that sign on the inside, is equal to 0. What happened to my 12? All right, it just disappears, right? Okay. So this grouping works because I have a common factor of x minus 1 in both of these terms. So this becomes x minus 1 times x squared minus 1. Each of those factors now gets set equal to 0. X is equal to 1. X squared is equal to 1, or x is equal to positive and negative 1. I just had kind of a repeated root in there, didn't I? That's all that said. Okay,
Why did you flip the sign on the second X box?
here,
Or, no, I guess it really doesn't matter, so it's the
well, because I cut that off with that set of parentheses, that positive had to change to negative. These two have to be exactly the same, and if they weren't, because you forgot to change the sign, that should have been an indication you did it wrong. Okay, all right, so I have these critical values here. And let's come in here. We're going to say, okay, I have a critical value at -1 and +1. And the first derivative test I'm going to run. What's the first derivative going to tell me?
Increasing or decreasing.
Very good, whether or not it's increasing or decreasing. So to the left of -1, what are we doing?
Decreasing.
To the left of -1, we are decreasing. How about in the middle
Increasing.
and to the right? Okay. So we are increasing on the interval from -1 to 1, and then again at from 1 to infinity. We are decreasing on the interval where? Negative infinity to -1, negative infinity to -1. And we also have what? This is where our extrema come in, right? So what do I know here? I have a minimum where?
-1.
All right, I have a minimum occurring when x is equal to -1. When x is equal to -1, what's y? Not really, because I already solved it, right? Oh, never mind. Okay, okay, so I don't have a max though, do I?
No.
No, okay. So we're gonna come back up here and we're gonna now take the second derivative. So if the first derivative was x cubed, so I can take the second derivative now. And I would find out that that would be 36x squared minus 24x minus 12, right? Set that equal to 0. Solve it. Let's factor a 12 out. 3x squared minus 2x minus 1, or 3x plus 1, x minus 1. Three x plus 1 is equal to 0, x minus 1 is equal to 0, x would be -1/3 or a +1, right? Those are possible inflection points. Those are the numbers that we're gonna use. Now, we're gonna come down here and we're gonna add to this chart that we're making. So we have a -1/3 now, which falls here in between. And we have a value at 1, correct? These are possible inflection points. What's happening to the second derivative to the left of -1/3?
Negative.
Okay, so we would be concave down. How about in between -1/3 and +1? Is it negative?
I think it's positive.
It's positive. Did I say left or right? I don't know. Should be positive. What's going on in the middle?
Negative.
What's going on to the, as you move across? What's next?
Positive.
Positive. So we're concave up from -infinity to -1/3, and again from 1 to infinity. We're concave down from -1/3 to 1. And we have inflection points, right? Occurring when x is equal to -1/3 as well as 1. Okay? Would I be able to know also, if we're getting the information about this function, at least what the y-intercept is? Can I find out from this function, the function we started out with, the y-intercept is? That should be the easiest one to find, right? Don't you just plug in zeros for x's? So I could find the y-intercept. I also know all of this information about where the function is increasing, where the function is decreasing. I know where the max and the mins are. I know where the function is concave up, concave down, and I also know where the inflection points are. So we can start to sketch a graph based on that information. That's what the curve sketching will be about Monday. Okay? All right, how you feel on that? All right, well, you've got your work to do then. So I want you to start by taking these three here. I have these 3 points, or these 3 functions here. I want you to start with these. And I'd like to see you determine where it's concave up, concave down, and possible inflection points. When you get one of them answered, come check it out with me.
So we're just determining the second derivative stuff, not the first one.
Well, that's a good. Just do the second derivative on this one.
Okay.
Feel free to work with other people if you'd like. All right, take a minute and write all three of these problems down, because I'm gonna turn this screen off in just a second.